And today's inaugural presentation, State of the Field, the Structural Health Monitoring Towards Infrastructure Resiliency with Erik Zuker of HNTB. Erik's a structural engineer in HNTB's New York Bridge Group. He's got more than 11 years of experience in the bridge industry. He's received a master's degree from Columbia, and he's taken on all kinds of roles at HNTB, including biennial inspector, designer of new and rehab structures, construction support services on major projects, and most recently in the owner's engineer role at the Governor Mario M. Cuomo Bridge. Throughout his career, a constant thread has been the application of structural health monitoring, advanced non-destructive testing, and the use of programming languages to evaluate large data sets. Erik, very happy to have you. Why don't you take it away?
Thank you, John. So as they mentioned, I am from HNTB's New York office, and I'll be speaking today on structural health monitoring, or SHM. Thank you to Professor Nassif and everyone at C2 Smart for allowing me this opportunity to speak. My intention today is to give an overview of structural health monitoring, as well as the way that it can make us better designers as engineers. I'll be speaking about the goals, as well as the value that it can provide. And I'll also be speaking about the challenges that we face in implementing this technology. I'll look at what HNTB has done in our practice for SHM, as well as case studies that we've included. I'll also speak about upcoming technology and that we see as promising. So in simplest terms, what is SHM? It's high precision sensors on physical infrastructure. Now you may be thinking this doesn't warrant an hour worth of conversation. However, when we start to look at how the data is collected, what we do with the data and how it's analyzed, it gets quite interesting. Before I dive in, I just want to say one housekeeping note. Today's presentation will be via Zoom. And so for everyone who's logged in via Zoom with both your email and your full name, you can receive the PDH credit from the Practicing Institute of Engineers. This is geared towards New York State. However, I've been told it will be applied to both Connecticut and New Jersey as well. There will be several question and answer segments during different slides, and a poll should appear on your screen for you to participate. And so SHM is an industry that's reached a certain level of maturity over the past decade or so. I came across an HNTB industry analysis that was commissioned back in 2011, and it spoke of a bright and gleaming future with greater computing power, cheaper and more ubiquitous sensors, as well as nearly infinite storage space. We now live in something very close to that bright and gleaming future. And so it's up to us as engineers to better understand how to use this data. We find the greatest value from SHM comes when it's integrated with other data sources. This could be better targeting our inspectors and our maintenance staff, integrating with weather data to understand not only safety, but also the loads experienced by the structure itself, and the traffic data, including WIM, to understand what live load is on the bridge. SHM can be a critical tool in the toolbox, but is far from the whole picture of the bridge. And so let's talk a little bit about the conventional sensors. Inclination or tilt is sometimes combined with acceleration. For instance, the CX1 from Sensor shown on the right side of the screen, which we'll talk about more in an upcoming case study. There's vibration, it's tracked by geophones, especially when we're putting a new substructure adjacent to existing substructure. Weather could be as simple as temperature, or it could be as complex as multiple anemometers and fog and rain to identify bigger weather conditions. Strain and strain gauges have long been one of the workhorses of the SHM industry, and we're now looking into new technology like vibrating strain gauge wire to add additional stability and a higher sample rate. Displacement obviously has great value when we talk about understanding structures. And so GPS can be used for long-term tracking settlement. Total stations, which utilize lasers, can get survey level accuracy automatically on various prisms on the bridge. And joint and bearing movement can be tracked by various methods. We also sometimes place corrosion sensors underneath the cover concrete to better understand how the rebar is behaving. Supporting all these types of sensors is ever more complex software and hardware. This has generally been wired with everything in local storage, but there are several trends on the software and hardware side. Things are moving more towards wireless sensors for data, and also low energy sensors, which can require a battery only every any number of years. Most of the data is also now stored in the cloud. Some cloud computing and post-processing also takes place. Based on all this, the goals of SHM are likely somewhat evident, but let's quickly talk through them. It is to better understand a structure, to capture the data and to store it, and then analyze it for both our current question and to save it for the future to analyze as new behavior is observed or new questions arise. It can be anything from a long-term system where the sensor is, this bridge is covered in sensors, or a very short-term application where we just have one specific thing we want to look into. As the engineers collecting this data, it is up to us to understand the context in which it is taken and the limitations and pitfalls of that method. It's important to convey this to not only our colleagues, but also our clients who are relying on that data. In the end, the goal is to establish a quantitative record for the future. And so value in SHM falls into a couple different buckets. The ones on this slide are more conventional, and the ones on the next slide are more the ways that it supports us and adds value as we're designers. First and foremost, we want to maintain safety on the bridge. This means tracking real-time operations by understanding wind at the deck level for safety of both trucks, regular vehicles, and pedestrians. The temperature, especially at the roadway, so that we can better identify freezing conditions, and also wind data, which Professor Nassif mentioned, to look at overweight trucks. We can use measurements ongoing on both the joints and bearings, so that our maintenance staff and even our biennial inspectors can be more proactive. And we can also look at identifying the long-term trends. The tilt plot below shows tilt in time series, and it's about 3 years worth of data. We see not only large thermal swings due to annual thermal cycles, but also a general trend in one direction. And finally, for the conventional types of value, we can identify post-event evaluation. This means value during, values experienced during the extreme event, as well as comparing the baseline data from before to the data shown afterwards. And so at HNTB's New York office, we work on complex bridge design. And so the advantages that we can get from structural health are not inconsequential. When targeted appropriately and applied correctly, the bridge can become something of an in situ laboratory. Now, this is a bit of an idealistic idea, but I think there's certainly some merit to it. In one example, there's the comparison to finite element models. Anyone who's done complex FEM modeling understands the boundary conditions and the material assumptions made significantly affect the output of the structure. By using SHM and observing the behavior in the field and comparing to that complex model, we can better align the boundary conditions. We can also use it to identify a load path, especially in complex structures. One simple example was a steel grillage that we had, and we had both a finite element model in the theoretical space, as well as strain gauges on the bottom flange to understand strain in the longitudinal direction. When trains passed over of a known weight, the response of the structure was about 1/4 in the field what we anticipated in the FEM model. What turns out is that a deck, which is intended to be non-composite during design, was actually picking up a significant amount of load. While this is a simple example, it speaks to the ability of SHM to indicate the way that load path can be better understood. This is especially important for complex design, as well as during complex retrofits. We're also able to better understand the response of the structure, both in strain, in tilt, and as also displacement. What we find is that in some cases, the annual thermal cycle puts the structure through a greater strain range than live load by an order of magnitude. And we can also understand the vibration analysis and the way that a structure dynamically reacts to both wind and live load. At the bottom of the screen, you see 3 of the codes that are the mainstays of our industry. These are the basis of everything that we do. However, we know that we as bridge engineers have jobs because we are able to apply these codes and then go a step beyond in more complex design. As we take those next steps and as we do our in-depth analysis, SHM can play a key role in understanding the way the structure behaves. And so this is our first assessment of learning. John, if you could prompt question number 1 poll, it should be popping up on everyone's screen. Question number 1 says, true or false? SHM is a term that only applies to a long-term whole bridge system. And so I'll give everyone a minute to answer that question. Let's see. Are we able to put up the results, John?
Sure thing.
And so we get an overwhelming false, which is correct. SHM applies not only to those long-term full bridge systems, but also to short-term applications. Question number 2, which of the following have seen significant advances over the past decade? Computing power, data storage, high precision instrumentation, or all of the above? Okay, and the results? 100% correct. Everyone got it. It's D, all of the above. And so I would be remiss if I didn't speak about some of the challenges. This industry has seen some advances with technology in the recent years, but we have not seen the orders of magnitude jump that have been seen in adjacent industries. It's only fair to talk about the challenges and what they mean. First, the sheer volume of data. With all of our sensors collecting at a high resolution pace, this can become overwhelming. We'll speak about this a little bit more in one of our upcoming case studies. Next, we have owners with a limited budget. There are a range of ways to invest in our physical infrastructure, from preventative maintenance, strategic repairs, and technology such as SHM. We have to make sure that we're utilizing and conveying a correct ROI, or return on investment, when we determine that technology is the best course forward. It has to provide either strategic information about major decisions, or help defer maintenance or defer full-term replacement on the structure to extend its life, or to verify the safety for the traveling public. There's also the status of adoption. We see below the adoption curve with the early adopters joining at the bottom, the growth phase, which is the steepest portion, and then saturation of the market. Different technology is in different places. We see that while the things like strain and tilt are towards the top, things like computer vision and machine learning, which we'll talk about later, are at the bottom. It is hard to get things outside of that early adopter phase, and there can be hesitancy to trust new technology. It's only through pilot projects and trying things in the field that we can bring technology up this curve. When reviewing a lot of SHM data, it is important to understand the messiness of real-world data. This can take various forms, such as missing or erroneous data, which could be related to a hardware or software issue, or even just a mounting issue out on the bridge. It can get hard, it can be difficult to assess what is going on when we see anomalous data, but by using understanding thermal interactions, looking at adjacent sensors, and even a field visit, we're able to better understand this. And finally, on this slide, the difficulty of maintaining technology on the bridge. The bridge is open to the environment and extreme weather, and in some cases is actually a construction zone. We can get around this challenge by building a robust system, by making replaceable components, as well as leaning on trusted monitoring partners who have experience in building robust systems. And we actually have another entire slide of challenges. They abound in this industry. Another challenge is taking technology from the lab to the bridge. We have some success in leaving that controlled lab environment to the more messy bridge itself, but it requires extensive field testing to take new technology and confirm its reliability on the bridge. This long time frame of development sometimes outlasts small companies with promising technology. There's also the challenge of collaboration between academia, the industry, and owners. These groups have different timelines and different goals, which is part of the reason that pilot projects to expand this technology are important. We also want to avoid a false sense of security when we have sensors out on the bridge. Having only a handful of sensors can tell us some things about the structure, but we don't want to overly rely on those sensors. We have to confirm that the failure modes that we expect to see in the structure will be captured by the sensors, and also that there will be an early warning sign, and so the thresholds that we have put in place will give us adequate advance warning if a failure mode were to occur or a negative issue were to occur. Next, we're limited by the physical realities. Now, I have the aqueducts from the Romans up on the screen, which HNTB unfortunately has not played a role in monitoring. However, I think they bring up an interesting point. The way we as a society move water is only 10% more efficient than the Romans did 2,000 years ago. And this speaks to the fact that some areas of our industry are simply limited by physical realities that cannot be overcome. And so we as engineers need to use judgment to understand what areas that we have for great gain and which do we not have areas for great gain. Next, there's limited data points. We know that we have a sensor on the bridge, for instance, a strain gauge in one direction. We have only one small piece of information. It's like looking at the world through a straw via that sensor. By increasing sensor density, we can get around this somewhat, but we do have to appreciate the limited perspective we have on the structure and what we're able to gather data on. And finally, as a challenge, over-reliance on technology. Trying to proceed in the challenges in the coming years without technology would be like trying to drive a car to town with missing a wheel. But relying solely on technology to implement these challenges would be like driving into town on a car with only one wheel. We need to be conscious of the ROI that the technology can provide and search for repeatable solutions. Technology companies like Google and Amazon have invested heavily in specific areas of our industry, like autonomous vehicles and alternative energy, but they've left major areas untapped. Things like asset management, risk analysis, fabrication of bridges, resiliency, and a holistic view of traffic from a big data perspective have not been invested into the same level as other areas. And now, what we at HNTB do around structural health monitoring. Much of our work is reviewing and analyzing data that comes in. This could be from an active construction zone or a structure where there are specific interest in its behavior or concerns. We can advise on strategic placement of where the sensor should be to capture the maximum effect, and we can also help interpret the data that comes in. We also advise on large-scale systems in both the planning phase and implementation, as well as operational protocol once the data finally reaches us. We do some work with readily deployed systems, and we largely partner with major monitoring companies to help install the sensors on the bridge. We also, in the vein of readily deployed systems, can utilize tilt and acceleration to understand thermal responses on the structure, as well as understand the vibration analysis and the implications of live load and wind. Using taut string theory, we've been able to look at the tension in lift bridges as well as suspender ropes. And we've been able to look at the way live load impacts various elements like light poles, fences, and even stay cables. Next, when a deck is being poured on a structure adjacent to live traffic, there are certain requirements for that must be met. And so we're able to use our technology to confirm that the vibration thresholds are not exceeded. And we also partner with several companies to do NDE, or non-destructive evaluation. On the right, we see the Olson Engineering signature impact echo device for mapping pavement. The first case study today is the Governor Mario M. Cuomo Tappan Zee Bridge. This is owned and operated by the New York State Thruway, was constructed by TZC or Tappan Zee Constructors, and the engineer of record was HDR, while the engineer of record for the main span was Cowie, Buckland Taylor. The people who installed the company who installed the structural health monitoring company was Geocomp, which we'll be speaking about mostly today. And HNTB's role was as the owner's engineer during the design, construction, and closeout phases. This is quite a system. It's largely a conventional system with sensors widely dispersed in a permanent configuration, and there's a greater concentration on the main span itself. The authority has numerous goals for this system, and so I want to talk through those now before I get into the specifics of the hardware and software. The first is to understand real-time operations and have a sense of what's on the bridge. Because this bridge is 3 miles long, no single vantage point can give you all the information, which is why we want to have sensors dispersed across. This includes wind at the deck level, as well as temperature in the roadway. The authority also wanted to establish a baseline of structural behavior so that if something were to occur in the future, we'd have a quantitative record to go back to. Using this, we can set up thresholds and identify changes in behavior for any one of the sensors on the bridge. If there's an extreme event that were to occur, it could be used as post-event forensics to understand the high resolution impacts of that event. It helps the maintenance staff of the throughway to be more proactive and identify joints and bearings that have issues. And finally, we're able to track long-term changes in structural behavior, as well as tilt and settlement over time. And so to talk through a little bit the way the sensors operate, they are all capturing data at a high resolution pace. And so this leads to more than 27 million lines of data that are captured every single hour. This can seem a bit overwhelming, which is why the system lays out 10-minute summary files that captures the max, min, and mean, as well as other statistically relevant pieces of information. There are random high-resolution samples that are taken for 10 minutes randomly once per day, and these are preserved indefinitely. The users can also trigger high-resolution data captures of 10 minutes, and in specific extreme events, when secondary threshold levels are exceeded, we have the ability, it will automatically capture that high-resolution data from the event and capture that indefinitely. We're able to get remote access via proprietary software that was put together by Geocomp from any New York State Thruway computer on the network. And the software, which you see the dashboard at the portion below on the screen, is able to give different indications in color codes, as well as create auto-generated reports, which allow us to track specific sensors in time series. It has the ability through the dashboard to make custom sensors and combine data sources from different sensors. And it also provides weather data to various APIs for use in other applications within the Thruway. On the hardware side, the system is set up to capture data even with a power outage. We have about 12 hours worth of battery life. And the data is stored locally in a high resolution format for at least 12 hours. So that if an event occurs within the past 12 hours, we can always go back to it and record that data. The typical data acquisition units were from Campbell Scientific, as well as a proprietary data logger that was created by Geocomp. The alerts are set in place at the local level, and the emails are actually initiated from that local level. The entire system is wired for reliability. And so to speak to the specific sensors on the bridge, there are 430 total, reporting 780 channels worth of data. This at times can seem overwhelming, but by using visual review of the time series plots, by considering annual thermal trends and comparing to baseline, using thresholds, it becomes much more manageable to understand what's going on in the structure and to achieve the data and the goals that were assumed. There is value in having this density of sensors because when something looks potentially erroneous, we're able to look at it from another perspective from a nearby sensor. The accelerometers are placed not only on the stay cables, which can help us understand the vibration of cables during wind events, but also at the towers to better understand the implications of a seismic event for the towers and the deck level, not only for various reasons, including to assess pedestrian comfort. Displacement is tracked at strategic bearings on the main span, as well as in every single joint. We have string potentiometers on both sides of the joints. Inclinometers are present at the towers, at the deck level, and every single one of the approach piers. There are strain gauges in the towers that can give relative change in strain to predict for the cables. Temperature is tracked not only at the roadway, which I mentioned previously, but also to identify steel ambient temperature and the air ambient temperature. Weather is tracked with dual anemometers, both ultrasonic and mechanical, as well as fog for visualizing visibility on the structure. Specific corrosion sensors have been placed as a spot check to understand corrosion on the bridge over time. Finally, GPS has been utilized to assess long-term tilt of the piers. When we do spot anomalies on this system, there are several ways to look at the data to understand it better. The first way of 4 is to look at long-term time series. This is often the primary form of review, and it's where we spot the baseline shift or anomalous data initially. Next, we can zoom in on the high resolution data and understand what is going on and also do a dynamic analysis if we feel it's necessary. Looking at temperature versus a specific sensor value in a scatter plot helps us to identify if it's following a similar regime that it has in the past or deviating from that behavior. And finally, the fourth way is to look at max min delta data, which means we're able to look at how much data, the range of data in every 5 or 10 minute period, which is good at isolating the responsive live load while taking out the impacts of temperature. Our next case study is the Marine Parkway Bridge, which was built in 1937 and is owned and operated by the MTA Bridges and Tunnels. It connects the Rockaways to the rest of Brooklyn and is one of the longest spans, vertical lift spans in the country. Years back, there was an upcoming rehabilitation contract for scour mitigation on the towers. The goal of our contract was to outline a baseline data set prior to implementation and construction to understand the range, both operationally and thermally, of the structure, as well as extend it into construction. This is a good example of targeted SHM, whereas the previous example had more than 400 sensors. This entire case study had only 4. It was important to have remote access because we didn't want to be driving out to the Rockaways to download data every time. And lift bridges themselves present a double-edged sword when we talk about monitoring data. On the one hand, they require a greater precision of tower plumbness because they have to operate in a specific way. Separately, they actually have a noisier operational window because of those very lift operations. And so these are the sensors. This is the CX1 produced by the company sensor. It can collect tilt at about 1,000th of a degree at a rate of 10 samples per second, and has an acceleration of up to 1,000th of a G. You can measure at 2,000 Hertz. It's highly robust in an environmental sense, and it also tracks temperature. The data acquisition units were present on the structure itself to collect that data, and the 4 locations are shown below in a schematic format. We had 1 on each of the main towers, as shown on the right, and we had 1 in the tower room. With these limited number of sensors, we were able to assess a number of things. Firstly, having 2 sensors on a tower helped us to understand if there was anomalous data observed, whether or not it was being shown by the other sensor on that tower, as well as large acceleration events. Separately, by having both the super and the substructure monitored, we could understand what was being attributed because of substructure movement and what was due to the interaction of these 2 systems. This is a very simple schematic of the system itself, with the CX1s feeding into the data acquisition unit, which went to a cell modem. This was uploaded via cell signal to an IP address, which we could then access. Everything on the bridge was wired, and it was universally accessible from any computer on the internet, including via an FTP site. This level of remote access was relatively new back in 2011 when this was first implemented. And this, I wouldn't quite call it cloud computing, but it's the early stages or the precursor to cloud. We were able to use the graphical user interface shown on the right, and we could also download CSV files and post-process them with both Excel macros as well as MapCAD. The high resolution as well as summary files were stored. There were a number of challenges in implementing this. The first was that it was a somewhat long-term deployment. The goal window was 2 to 3 years. And so while it doesn't quite fall into the permanent range, it's also not a short-term deployment. So we had to thread that needle of making a robust enough system to last that amount of time. The environment was harsh, as there were exposed to the elements, were very nearby salt water, and there was ongoing maintenance activities. There was one time, shown in the plot below, where there was a noticeable baseline shift which had not been observed previously. When we initially witnessed this, the first thing we did was look at the other sensor on this pier, which would be at the substructure level. The baseline shift was not observed there, which led us to believe it was either part of the superstructure only or something locally occurring at the sensor. We were able to find that the sensor shown here as a tilt baseline also had a major acceleration event during that same time frame, whereas that was not reflected by the other sensor on the pier. And looking back at maintenance records, it appears that someone from the maintenance team accidentally bumped or dropped something on the sensor, and it changed this, so just those 0.2 degrees within the mounting. And so by doing the detective work, we were able to better understand what had occurred. Determining the significance of changes when they're observed can be a challenge with structural health monitoring. The plot on the right shows the typical dashboard that we utilize in the Excel macros. The top plot is temperature. The next 2 plots are X and Y for a specific sensor, with both the mean data as well as max and min shown throughout. We did have a power loss event in the middle of this time frame, which we were then able to rectify. And one interesting note as a minor case study within this one is the 2011 Mineral, Virginia earthquake. This, some of you may remember, affected a number of bridges in New York and was felt in New York. And so by looking at the data that was experienced during the event, we could confirm that both the accelerations and the tilts that occurred were within the operational window that was already observed both from thermal loads as well as a movable lift. And so we were able to confirm that there was likely no damage to the structure. And so as I mentioned, operational precision is key for lift bridges, which is part of the reason for this structure. The thermal response we found was significant and was not always linear, which meant that we needed a longer baseline period to collect data on. The plot below shows a prediction based on linear extrapolation. This is almost a precursor to machine learning, if you can call it that, back in 2011. And we utilized a linear line of best fit to estimate where the data would be. So the data prediction is what's shown in red, while the blue is the actual data. And there's some correlation between these two. Finally, for the Marine Parkway, we had to look at both the implications of both time as well as temperature on tilt. Shown in 3D on the right is a cube that could be rotated in 3D space in the MathCAD file. And the three different 2D plots are shown on the left. The first one being time and temperature, essentially output from a thermometer. The next one is temperature, time, and tilt, which is the output from a inclinometer. And the bottom plot is the tilt versus temperature, which shows that clean linear regime of response from the sensor itself. We could determine that if we went outside this regime in any significant way, we knew we'd have a change in behavior outside of the thermal response. Our next case study is the Verrazzano Narrows Bridge. This was built in the 1960s and is also owned and operated by MTA Bridges and Tunnels. It connects Brooklyn and Staten Island and is actually the longest span in North America at 60 feet longer than the Golden Gate Bridge, which I can't help but think is no accident. This is an example of utilizing information from inspectors and our monitoring system as a two-way street. In this case, there was potentially constrained joint movement, and so we wanted to go out there with a quick and readily deployed situation with sensors to better understand. We again used the CX1 from Sensor because we had those ready to go in the office. I talked about some of the specifics of the specs, but the advantage here was that the data fed right into a laptop. It was locally stored, and we didn't have to worry about power because we only took the range of time based on the laptop battery life, which greatly simplified logistics. And so this application took only 4 days in the field for 2 engineers, and we were able to utilize daily thermal trends to assess the thermal response. The goal was to identify asymmetrical behavior within the structure, as well as any potential interaction between the superstructure and the towers themselves. We put sensors at the deck level, the hangars, and at the tops of the towers. It was a challenge to identify the best location, especially at the deck level, because the vibration from vehicles had some impact on the tilt because it was such a highly precise instrument. Everything we collected was supplemental to manual measurements that were taken and observations that were being currently taken by the biennial inspectors. One challenge was the variable temperature. While you assume that the temperature would get constantly warmer throughout the day, it actually got colder during some days because we had cold fronts move in from the ocean, which is right there at the Verrazzano Bridge. There's also a lagging thermal response, which means temperature and tilt are not always tied together because it takes time to heat up the structure. And also because the sunlight, if it's a main driver of temperature increase, changes the way that the structure would eccentrically get loaded on one side. And finally, the challenge of battery power, which was a limiting factor. In the end, we were able to confirm that the towers and the roadway showed no significant tilt trends in response. However, by looking at the hanger pins, which we were able to, which are almost an order of magnitude shorter than the tower itself, we saw a greater tilt response from the thermal changes. The plots below were the main takeaway, and we see that one location is about 1/6 the steepness of the other, indicating a asymmetrical behavior change in the bridge. This all goes to point out that readily deployed systems, especially using thermal responses, have the ability to provide real-time or near real-time data. And so with those three conventional case studies, we've really covered sort of the basis. A conventional permanent system, a very targeted, somewhat permanent system, and a readily deployed system on the bridge. And so now the next assessment of learning. True or false? Ambient temperature changes can create deflections and stresses within the structure. Okay, and the results, John? And overwhelmingly true, that is correct. Question number 4, which of the following is the best way to handle potentially erroneous data? Field investigation, review thermal trends, evaluate adjacent sensors, or D, all of the above? Okay. And the majority of people indicated D, all of the above. That's correct. And I'd also add that software and hardware challenges should also be investigated at the same time. And so now I'd like to speak a little bit about upcoming technology that we at HNTB see as promising. The first is computer vision. Utilizing smartphones or security camera footage, we're able to post-process and detect displacements of structures in real time. This is done by tracking pixels, changes at the pixel level between frames of the structure. OpenCV is the software that we use with the backbone of Python, and OpenCV comes with several open source trackers. These are largely geared towards tracking something like a car moving across the screen or a face moving across the page. Because the appearance of the structure does not change nearly as much as those types of items, we've actually utilized some proprietary trackers via as HNTB that we've used to track displacement better. And this would look at something such as the interface between light and dark, between the sky and the girder, as you see here, to track the centroid of that interface from frame to frame. One of the main advantages of computer vision is not only the fact that we're able to collect a lot of data very cheaply and analyze it just as cheaply, which is free. We're also able to track various points on the structure by looping the video through numerous times. Instead of looking at a single sensor that's been placed on the bridge, we're able to look at the various points on the structure. There are a number of challenges when we talk about computer vision. One can be, with field applications, there's issues with glare, as well as changing field conditions with lighting from day to night, which is why we typically stay towards short-term deployments. Ideally, you have a reference point within the frame, and the camera is positioned perpendicularly. By looking at something of known size within the frame shot and in a similar plane, we're able to turn the pixels that we see into actual measurement on the bridge. We can camera shake can also be modified by taking specific target points that we know are stationary within the structure. Minor signal processing or smoothing is sometimes required just to take out some of the vibration of the camera itself. What's shown on the screen here is dynamic behavior from a bridge that we were able to track. And not only could we find the displacements, and this is shown in pixels, but we were able to convert later to inches. We could also identify the fundamental frequency at which the structure was reacting. Another promising technology is digital image correlation. This uses dual cameras on a mounting bar, as shown on the right, and uses similar technology to how your eyes use bifocal data to better get depth perception. What we used was highly robust adhesives that had a randomized pattern and were placed on the structure itself. This method is portable, and it's also non-destructive. It has no leave behind of sensors or wires. We simply point the cameras at the robust adhesives and capture photos that we can then post-process. This allows us to get 3D full field strain and displacement on that member of the structure. All the work we have done so far is via, in partnership with Notre Dame, Dr. Ashley Thrall, as well as one of her students, Yao Wang, who is a PhD student. This has been used and is ideal for construction and repairs, where we're tracking major changes in structural load over the life of the structure. It can track at about 1 KSI at a granularity, depending on application. This has been used in the field by HNTB at both the Governor Mario Cuomo Bridge, as well as the Delaware River Bridge, which had a fracture and subsequent closure in 2017. And next, as an upcoming technology, machine learning. Now, this is sometimes called artificial intelligence or AI, and has been a buzzword for quite a while in our industry and seems to now finally be taking hold. This is a broad topic, and so covering it in a single slide would be optimistic at best and foolhardy at worst. But instead of talking about sort of a pie in the sky, where will we be in 10 years of machine learning, I want to instead open up the hood and understand what's going on behind, as well as the pitfalls and challenges that we see. In simplest terms, it's taking data, making a statistical prediction, and rendering a decision, a variable probability for that decision. Now, this could be something using simple linear regression or a much more complex neural network. We've used packages like scikit-learn, which is relatively simple in Python, as well as TensorFlow, which is what Google product with an interface of Keras, which also runs on Python. When predicting this, using these softwares is important because they're not only free, but they're also democratized and have huge user communities to troubleshoot errors or flaws that we get. It can be a challenge to get a clean data set. And in fact, much of our time when we're implementing machine learning is post-processing and cleaning up the data to remove missing data segments, as well as removing potentially erroneous data and understanding where our data comes from. It's important when you start machine learning to go in with a problem to be solved. Instead of looking for simple correlations, which there will always be some, just based on random chance, we want to have an answer, we want to have a question that we have and an answer that we're seeking. It can be a significant challenge to look at the black swans or the edge cases within machine learning. These are areas where we have a very rare occurrence and can complicate the way that we predict specific data. There's also the significance of error rate. In the machine learning industry, a 95% success rate or probability accuracy is considered good. However, in our industry with bridge design, we must be right 100% of the time. Reconciling those two methodologies falls to the bridge engineers and the structural engineers who choose to utilize machine learning. We also have the challenge that this can be a black box, similar to the complex FEM models that we sometimes run. It's important for a senior engineer to review the data that is output, as well as use simple hand checks to confirm the accuracy of data itself. In the same way that Excel changed the way that we as engineers do calculation sheets 30 years ago, machine learning is poised to help us better understand and become better engineers, not to replace us, but to augment our abilities. There are numerous applications that have evident gains from machine learning. One would be finite elements. We talked before about utilizing SHM data to better hone boundary conditions and properties of the model. We can similarly use machine learning in the future to better hone those characteristics and to match actual data. We can use it with structural health monitoring data, not only to assess validity of what we're finding, but also to look at predictive thresholds, which we'll talk about shortly. And there's also the use of machine learning on inspection data to help us better understand deterioration over time, as well as to make our inspectors in the field better. And so one of the greatest challenges for anyone doing machine learning, doing structural health monitoring, is to assess how to place your thresholds. If you make them too tight, you end up getting way too many alerts. And if you make them too broad, you end up finding that you don't get alerted in time to a change in structural behavior. The plot or the pane on the left shows typical data, let's call it tilts, in blue, and large threshold gap in green. This might be necessary because of a large thermal response from an annual cycle. By utilizing machine learning, we can look at not only the temperature, but also the values of adjacent sensors and predict what should be occurring or what position that sensor should be at. We can add a small statistical spread, which leads us to the orange threshold shown below. They track where the sensor should be. And so any anomalous behavior, as shown to the right, that blue spike, will be spotted much earlier and allow us to get less thresholds, as well as earlier identification of behavior change, which is key for risk mitigation. This is still in the proof of concept phase and is not intended to replace conventional thresholds, but instead be a secondary threshold methodology to better assess the structure. This goes well beyond temperature correlation because we're implementing the values of other sensors. It has value for complex structures like stay cable bridges and movable bridges, which may not relate directly to thermal response. It does require a specific density of sensors to provide value, and there's a challenge of missing and erroneous data, which can throw off algorithms. These algorithms take a lot of computing power, at least in their current format, and so it'd be something where a report would be run, not a constantly operating system, most likely. And now our final assessment of learning. Question number 5, true or false? Computer vision requires a dual camera setup. And let's see the results. So this one's actually split between computer vision, and this is a bit of a trick question as well. Computer vision relies on only a single camera to take the data, whereas digital image correlation, which has the ability to track strain, full field 3D strain, requires a dual camera setup. Question number 6, machine learning has the ability to A, refine SHM thresholds, B, augment inspection abilities, C, identify critical findings from a large data set, or D, all of the above. And the results. And this one overwhelmingly is D, and that is the correct answer. Finally, I want to touch on some industry trends that we're aware of. This will be both specific technologies as well as a 30,000-foot view. The first is pavement condition survey. We're seeing numerous methodologies to implement a more quantitative review of pavement over time. And this is meant not to replace, but instead augment what we're being captured qualitatively by inspectors. This human algorithm interaction we see as key. And while pavement is likely the easiest application because we can capture it so linearly, additional methodologies for tracking other elements is likely right around the corner. Drones are already changing everything we do, and they're poised to have an even bigger impact. With longer battery lives, lighter instrumentation, as well as legislation that's progressively moving forward, drones plan on drones having a major part of our industry. Next, there's mobile SHM applications. This could be a suite of sensors that can be held by an authority and ready to deploy at any minute to capture specific strategic information on a bridge. Next, there's this idea of data for sale as a new paradigm. This is an article shown on the top left from Bloomberg from back in April. It talks about ways in which we can, data can be sold to insurers, financial analysts, or other authorities to help them better understand economic indicators, as well as to better assess insurance risk. And finally, locusts. You may have thought we wouldn't be speaking about locusts today, but you would have been wrong. This story from the New York Times speaks about an app that was used in East Africa to track not only the location, but also the density of locusts. It was used to do more targeted mitigation and was considered a huge success story in better serving the people of East Africa and eliminating this threat. While I hope we don't have any locusts to deal with here in the New York region, I do think this idea of using open source information, using crowdsourced apps, as well as just alternative information in general, is something we should continue to consider as we serve our clients. And now from a 30,000-foot view, if you've paid attention to nothing else, please pay attention to this. As I see it, there's a confluence of 3 great trends that will affect our industry and make the challenges of the next 20 years look nothing like the last 100. How we handle these challenges will have echoes through society at large. The first is an unprecedented demand on our infrastructure. Sea level rise, as well as increases in temperature, get the most press. However, we know that there is increased rainfall intensity and inland flooding, like we saw with Hurricane Ida, as well as a wider range of temperatures leading to bad conditions such as wildfires out west. There's heavier trucks, as well as platoon vehicles that will change the way that our infrastructure experiences load. And the pandemic has also changed the way that we see demand in both people and goods, increasing in some areas and reducing in others. The next great confluence is complexity. When the Brooklyn Bridge was completed, all of the closeout documents could likely have fit in a single desk drawer. And yet today, the complex projects we complete have millions of pieces of information that are difficult to track and search in a digital format, stored on a SharePoint site. These complex systems are also becoming more and more linked, which means there are interdependencies which may not be immediately evident. The institutional knowledge to track these documents, as well as the interactions of systems, can be very difficult to preserve. And finally, the third great confluence is technology and how we use it. There are many areas where technology can be applied, and we've talked about some of them today with SHM as a lens. By using pilot projects, trying things in the field, having specific goals, and considering the ROI and the common sense of each application, we can help implement technology and make it a critical piece of our response to these upcoming challenges. The complexity of modern times has created numerous expertise silos that are only getting higher and higher. It's up to us as the engineering community. We bear responsibility for connecting these various silos. And so what does that look like? It means industry collaboration between academia and contractors, consultants, and owners. These are groups with different timelines, different goals, and sometimes it seems like different languages. And yet as engineers, we are one of the only groups that speaks consistently to all of these other different groups. I often say the iron worker and the professor rarely talk, and neither of them talk often with the owner. And yet all of these groups hold key pieces of the infrastructure puzzle for the future. We can be a link between these disparate groups. And so I'm not suggesting that engineers go outside their lanes. I, as a bridge engineer, am not qualified to design a wastewater site. However, we do need to be able to talk to people in adjacent lanes and even take the onus for starting those conversations. Multidiscipline used to mean that an electrical engineer, a traffic engineer, and a bridge engineer would sit down together. Today, it means we have a data scientist, an NDT expert, a city planner, a risk analyst, a climate scientist, and a bridge engineer sitting down together. I look forward to the way that our industry adapts to these changes in the future. I'd like to close by acknowledging several people who made this presentation possible. Vic Wog and Samir Salah from MTA Bridges and Tunnels, Jamie Barbas, as well as Rajesh Taneja from the New York State Thruway, at the Governor Mario M. Cuomo Bridge Project, Professor Nassif from Rutgers, as well as everyone at C2 Smart. Thank you.
Erik, thank you so much for such an interesting, thorough presentation. Truly a state of the field, worthy of the inaugural event in our series. We have about 3 minutes, so we can go over a little bit, but I would encourage everyone in the audience to ask your questions either via the Q&A button at the bottom of the screen, or if you raise your hand, I will unmute you and allow you to ask your questions directly of Erik. We have one that has come in, Erik, which is just about the battery life on the CX1s. You mentioned quite a while back. How's the battery life on these devices?
Yes, so the CX1 is actually just a sensor itself. It requires an external battery source. And so these are used sometimes in a long-term application where they receive direct wired power, but they can also be used like our Verrazzano case where we apply them to our laptops and we got the entire life of the laptop battery, which in our case was about 4 hours to collect data.
Okay, so this one comes from me actually. So you mentioned a lot about the everyone kind of working together and not just staying in their adjacent lanes. So in your experience, talking to us at the C2 Smart Center, where do you want to see additional research dollars and research time go to make the largest impact on our infrastructure resilience in the future?
Yeah, so I think one great way, and I was going to mention this, but I forgot to, is that we're sitting on a treasure trove of data. There's so many things that we're collecting, types of data we're not even properly utilizing. Be it WIM data that I know at C2 you guys have dug into quite a bit, but some authorities have not adequately explored the depth of their WIM data. We have a lot of SHM data that sometimes just sits on the server, and even the alternative data sources, like I mentioned with some of these apps. I think that the best way we can move forward is these types of research endeavors to better understand the data we already have, as opposed to going out and trying to explore new data sources.
So I'll just use this opportunity as a segue, actually, because our next event in the State of the Field series is going to be on structural health monitoring on the Brooklyn-Queens Expressway, for which Professor Hani Nassif will share the methods, challenges, opportunities, and latest news on the C2 Smart Center urban roadway testbed right here in downtown Brooklyn, and how we're going to implement the latest structural monitoring technologies. That event is going to be on Tuesday, November 23rd. Back to the questions, though. What is the average annual cost for this SHM system you've been talking about, Erik?
Yeah, so it's highly dependent on which system that's put in place. I unfortunately don't have any specific dollar numbers in front of me. What I would say is key is to understand the scope of the system required and to make it targeted if possible, so you're not collecting data you don't need, but also utilizing all the data you have at your fingertips, because many times once the system's installed, you'll find new ways to use the data that you weren't even intending on the front end.
Okay, so this next question, are there any data or studies you've worked on the effect of footwalker vibration-induced effect on bridge performance?
Yep, so we have used our CX1 as well as the GP1 by sensor in numerous cases to evaluate not only pedestrian comfort. There's certain established thresholds for when a person begins to feel uncomfortable on a structure, but we've also used that to assess the way that the load from foot traffic can be put into the structure. You know, historically, when armies used to march across bridges, they always had to break lockstep, because there were cases where their constant repeated pattern would feed into the fundamental frequency of the especially suspension bridge. And so mapping those things and understanding that is something we consider during design. And of course, retrofitting on the back end. We've all seen that video of the Millennial Bridge in London and the vibration from pedestrians. Tracking it on the back end once the structure has actually been created and adapting and retrofitting if necessary is important.
Okay, we have time for about one or two more. This question is, have you been partnering with FHWA on the installation of these SHM systems?
Yeah, so none of these systems that I mentioned today were specifically related to FHWA. You know, our primary interface at HNTB is with the owner of the infrastructure. I know some of them have interacted with FHWA in different capacities along the way, but nothing we've done to date has directly fed into FHWA.
Okay, and I think we'll end on this last one. So Erik, you can't help but feel a little optimistic in some ways about the possibilities of all the new technology that you've mentioned today, what the benefit will look like. Can you just reiterate that pie in the sky utopian vision of infrastructure resilience that you've kind of gotten to before, and just quickly detail, like, what are some of the challenges to making this best case scenario happen?
Yeah, I think, you know, sometimes feels like day to day I swing between both being a tech optimist and a tech pessimist. I think there is great opportunity, and the time has never been better. There's so many applications and things in other fields. You know, much of the tilt data that we have is because it's been pioneered by the smartphone industry, and we're now able to take that technology and apply it to ours. And so there are really good reasons to be optimistic, but I think it's important to understand how the context and limitations of technology as we pull it into our industry, and to not have too optimistic hopes until we've been able to prove it definitively on a structure via using strategic use cases.
Okay, I can't think of a better way to end it. Erik Zuker, thank you so much for participating. We had a great crowd today, so thanks everyone who's come. If you're from industry and audience, and industry and agency audiences, and you're interested in funding a research project or meeting with C2 Smart Center to expand possibilities for our next year of funding, I'm going to send a follow-up email to everyone here in attendance, and you can take a look at our pre-RFP. Our next event in the series, as I mentioned, is going to be on Tuesday, November 23rd, with Professor Hani Nassif and his team on structural health monitoring on the BQE. If you enjoyed this webinar, definitely follow us on Twitter and LinkedIn, join our mailing list. Erik, thank you so much for being with us today. Hani, thank you so much for your introduction and for being with us today.
Thank you, John. Thank you, Erik. And thank you, everyone, for attending. Have a wonderful day. Thank you.
All right. Thank you so much.
Bye.